All right, another quickie. A couple of people have mentioned COVID testing errors. Oh, it just won't die. All the conspiracy theories, I understand, I get it. Yes, fear, uncertainty, doubt, anxiety. And people want to know that if we're spending a lot of money and time and effort doing these tests, that it ought to be reliable. So, of course, we get alarmed when we read headlines that say things like COVID tests are unreliable or only a third of them are any good, which I couldn't find myself, but I keep hearing it. So I think it's a misunderstanding that people have taken by conflating or equivocating a few words that ought not to be. So this isn't specifically about COVID, but science application and errors, and a very quick mention of the things that go on behind a single quoted number, and a hint at regression analysis and maybe confusion matrix if it's not too long, which actually leads into machine learning and so-called classifiers. So just to cover off a few basics, it seems many a time a junior journo or a blogger gets hold of a couple of facts or data points and misinterprets them and misunderstands terms and jargon, or doesn't get the maths, and they reach for a sensational headline that misrepresents the truth of the matter. Then Facebook groups get hold of it and then bastardize it into a grotesque straw man beyond recognition. Then it does the rounds. I mean, I'm all for asking questions. I mean, it's great, you learn new things, but, you have to be open to the idea of learning new things. I mean, it's like an acid test. I always say, when an expert, specialist in the field, comes out and says something that I don't agree with or that I don't think is right, the question I always ask myself is, what do they know, being a domain expert, that I don't? It's not to say, what is it that they think that they know that is incorrect that I actually know? It's the wrong way around to do it. Again, I get the feeling there's a lot of anxiousness around this. Have they thought of this? Have they thought of that? Yes, they have. Yes, I mean, if you've thought of it, they've thought of it. Not because they're clever, it's just they do it 50 hours a week. You and I do it maybe half an afternoon on Sunday between lunching on blogs and reading the internets. They've thought of it. This is tricky stuff, and often science has words that have specific meanings in the field. But we also use these words colloquially, sometimes to sound smart. For example, the one I have a bugbear about is theory. It's just a theory, they say. It's a dishonest conflation, and I won't have it. What they mean to imply is that the theory in question is the same as an idea or a notion that can be thought up for no reason by anyone and therefore isn't really valid. It's just an idea. And with that, they attempt to hand-wave away what a theory actually is. Gravity is just a theory, they say, as if that diminishes it. So I'll get onto data and facts and evidence in a minute, but a theory is the most comprehensive description of knowledge. A theory begins with a hypothesis that contains testable claims that has had those experiments conducted to establish the reliability and accuracy of such claims. Within the theory is a mechanism that can be used to verify or falsify the claims and hypothesis. And if those tests and experiments have failed to have falsified the claims, then the idea lives on. It will be killed if a test can be devised that shows the claims or the hypothesis in the theory to be wrong. Surviving that, the theory has to explain and account for the observation of the phenomena. It is a verifiably accurate explanation with practical application and predictive utility. Often it will also include natural laws themselves, summary statements or equations that have been devised to describe the nature of cause and effect between observed elements. But also, caution, theories can only be disproved. They are not themselves proof. Again, this seems to be one of those notions that many don't seem to grasp, because the idea of it not being proof somehow leads to a conclusion that, well, it must be false then if it can't be proved. It's not how it works. There's a subtle difference. So having said that, theories are the frameworks and models of things that are as close to certain as we can get, yet, as stated, contain within them a mechanism to falsify, and with the constant testing and challenges of new information to test in new ways, remain unfalsified. And the other one that grates my gears is research. Do your own research, for fuck's sake. Research, proper and real research, is the endeavour of discovering new phenomena previously unknown to the entirety of mankind. It's not learning something that's new to you or new to me. Learning of something that someone else had already discovered, that's called reading. Real research is hard fucking work, often expensive, and frankly, a lot of the low-hanging fruit has already been picked. It's really hard to find and discover something hitherto unknown to the entire knowledge of mankind. It's tricky business and expensive, and you need a lot of people and lots of labs. Right, that being out of the way, COVID tests, for fuck's sake. Sensitivity, specificity, and predictive values. Ugh. Alright, so again, before even getting into that meaning of words, colloquial and scientific, what is meant by the word test? Are we talking about diagnostic tests or screening tests? Hopefully that ends the argument. Alright, crass example. We can do a screening test and work out quickly, say that 60% of a nation is obese. From this, we can realise that there is likely a systemic issue. We might not know what that is, but we know there is one. Would we then tell everyone to cut down on stuff in their faces? No. Immediately, we think that this is inappropriate advice for the other 40% of the population. Wrong again. It may be that the other 40% is actually on its way to being obese if they don't cut down on the food. They're going to get there pretty soon. It may also be the case that a significant portion of the 60% classified as obese has realised the issues and has already cut down on the crisps and chips and will soon not be obese. How can we tell? Giving advice without diagnosis is called malpractice. So a screening test looks for risk factors that are indicative of some existing or future condition. A diagnosis test looks to see if a specific condition is present with 100% accuracy. Now, well, that's possible. No, I'm not sure. Again, I'm not a physician, but by way of example and for illustrations purposes only, we might take people's height and weight and from that establish a fast guess likelihood of diabetes. Fast screening. We might then invite people in with a certain BMI threshold and over a certain age to come in for a diagnostic test. So while it would be inappropriate to use a screening instrument to make a diagnosis, a screening instrument that has high false positive isn't necessarily a bad thing, nor unuseful. Indeed, the limitations and the applications of these tools are well understood and they're well known. Yes, they've thought about it. They know the profile of these instruments. They know when it's appropriate to use and when it's not and how they're to be used and so on. Alright, with COVID, a little bit different since this is a novel virus, something new we don't yet know and are constantly re-evaluating as new information comes to light, new patterns come to light. I'm wondering, for example, if some journo or blogger has heard that screening tests have low sensitivity or specificity and has jumped to a conclusion about what that means for diagnosis. Or when it may well be, it's a different test altogether for diagnosis. In other words, they only heard the word test, low sensitivity, and didn't appreciate that this is for screening tests and that diagnosis tests might be different. So yes, screening tests are well known to be imperfect and sometimes ambiguous, but they are often fast and relatively inexpensive, and as such it would be preferable to yield false positive. The diagnosis would then confirm or not. Now I don't know, but these are the questions to ask and get clarity on. Now from here now it gets a bit more complicated. So, sensitivity, specificity. Alright, reading this one off the website. Clear definition of sensitivity would be a screening test's probability of correctly identifying solely from among people who are known to have a condition, or those who do indeed have that condition, i.e. identifying true positives, and at the same time not categorising other people as not having the condition when in fact they do have it, i.e. avoiding false negatives. Alright, yeah, that's a bit of logic to get the head around. And it's often abbreviated to positive accuracy, but the avoiding false positives is also part of it. Specificity is the ability of a screening test to detect true negatives correctly, identifying people who do not have a condition. And again, it's a probabilistic thing. And the other thing to notice about this is that sensitivity rates and specificity rates are pliable. This means that if sensitivity of a test is increased or decreased, there may or may not be a change in specificity. They are not coupled. So a gain in one doesn't necessarily mean a loss in the other. Might not. Pliable. Okie dokie, leads on to our next two. PPV, positive predictive values, and NPV, negative predictive values. PPV is a screening test's probability when returning a positive result of correctly identifying true positives while also not categorizing some people as having the condition when they do not. NPV is the screening test probability when returning a negative result of correctly identifying true negative while also not categorizing people as not having the condition when they do. Right, so sensitivity and specificity are concerned with the accuracy of a screening test relative to some reference or a benchmark or so-called gold standard, i.e. it's to do with the accuracy of the test, and I'll talk about accuracy in a minute. The PPV and the MPV are where people's condition is being assessed. So again, the sensitivity and specificity are concerned with the accuracy of a screening test relative to a referent. The PPV and MPV are concerned with people's conditions that are being assessed. There's a subtle difference. So this is why a screening test with a high sensitivity and low specificity is selected, then followed up with a diagnostic test where high specificity and lower sensitivity can be used. And I'm told by a bio-nanotech chap that microfluidic based bioassays are the best performing, but by far from being mass produced and cost effective trade-offs, as always. As to the claims about 80% false positive results, I couldn't find any. I've heard a couple of people say this. I really couldn't find any. But I did read some stuff that was poorly worded that alluded to 50% chance of false positives and 16% false positive results. I'll come on to that in a second. But the chaps in the white coats have lots of metrics they use to talk about this stuff. We're going to go through a few and get into a bit of maths. So let's consider a situation where we have a population of 10,000 people, and let's say somehow we actually know the prevalence of the disease that we're interested in testing for. Let's say it's 5%. This way we know that 500 people out of 10,000 have it. Now, if the sensitivity and specificity of our test are rated at 95% and 99% respectively, we can do a few numbers, and we can get a few ratios out. So given the sensitivity, our test is predicted to find 95% of those 500 who have the disease, which is 475 people. This is the true positive number. It's a number, not a rate. And I've seen some websites quote things like true positive ratio. I think it's not, it's true positive, it's a number. Anyway, given the specificity, our test is predicted to find 99% of people who do not have the condition tested for, which is 9,405. This is our true negative number. The accuracy of this test is given by the sum of the true positive and the true negative divided by the total population. In our case, it comes out 98.8%. Wow. So as I said, there's lots of other ratios, false discovery rate, positive predictive value, false submission rates, negative prediction rate, false positive rate, among others. The false positive rate is the probability of a false alarm and is calculated as the false positive number divided by the false positive number plus true negative number. So in our example, with a given prevalence rate and the sensitivity and specificity, the false positive number is 95. If you think about it, this is the specificity multiplied by the population multiplied by the prevalence, because it's a number 95. The true negative number, we already know, 9,405, Hence our false positive rate is 10%, 95 over 9405 plus 95, which is 9500, so 95 over 9500, 10%. However, so I've seen a couple of websites seemingly confuse false positive rate with another ratio called the false discovery rate. I'm not sure whether this is a bit of confusion or loose writing or fast writing. I'm not quite sure. So you can imagine, as the prevalence increases, there's less people without the disease that we're testing for, which means that the number of false positives decreases, and so does the number of people without the condition, which means true positives go up. That's what it means. This rapidly changes the false discovery rate, which is given by the false positive number divided by the sum of true positives plus the number of false positives. At a 5% prevalence with the sensitivity and specificity as stated, the FDR is 16.7%. However, if we change the prevalence to 1%, the FDR leaps right up to 51%. So I'm not sure we actually know what the prevalence rate is. So, as data comes in, figures revised, and it's why it's important to keep on testing. So we know that we've tested a lot of people, and we know how many cases are tested positive. But what we don't know, and this is where the stats and the bean counters go crazy for it, with all their modelling and extrapolations, linear regressions and all that. But what we don't know is how many people are at home, for example, sick or with mild symptoms that have not been tested, and they don't know and we don't know that they have it. Hence, the government sending out carefully selected test kits. Come on to sampling in a minute. So there's a bit of leeway in this number, and this is, again, I suspect where we can, if we're writing blogs, we can take a pessimistic or optimistic view to conjure up whatever number. So, we can, I don't know, maybe we can guess between 0.5 and 5%, and that might not be unreasonable. So, for example, today, July 22, known cases in America, 3.9 million out of 320 million. That's a 1.2%. And that would yield an FDR of 46%. But remember, number of cases isn't necessarily prevalence rate. And then what do we mean by prevalence rate? Is it people that recovered, or is it, all the people that have it? You've got to be careful that you're taking the right number. So going on to the Johns Hopkins and seeing how many people have been tested and confirmed to have it isn't necessarily the prevalence rate. You might argue that those people who, you have to take out the 200,000 people that have died because they're not going to be in the stat. And, what about recovery rates? And then you get into questions of, yes, it does seem like the antibodies stay around for a while and that immunity lasts, but for how long? We don't know. Again, novel virus, we don't know. There are stories of people catching it again, let's put it that way, but these seem to be anecdotal stories rather than actually hard data. So again, I assume that the boffins are getting all this data and crunching it all. And you can imagine my concern that nationwide data is now being funneled straight to the White House rather than the CDC, who do this kind of thing all day long. It's what they do. And you can see my concern that with all these acronyms and accidentally or intentionally saying false discovery rate when we meant false positives, or when we meant false negatives, and we actually accidentally quote the negative prediction value. I do have concerns. Needless to say, I hope that the policymakers and the analysts at least get access to the raw data to wade through it all. But then, policy is only made on the information you're given, and the analysts only work on the information they're given. Here we are. One thing to know about scientists, real scientists, real ones in the field actually doing work, is that they are experts in error. Books have been written on error analysis. Even the length of a bit of string is not so straightforward. It's the old coastline problem. The finer detail you add into your measurement, the longer it becomes to a finite point. It's one of those things of fractal geometry. But suppose that you want to work out or do an experiment to work out what the force of gravity is using a pendulum, and it's a well-known experiment. And we can do this. And according to a well-known formula, it links the length of a pendulum and the timing for a full swing to be able to calculate what gravity is. So let's consider, do you measure the length of string, if you are using a weight on the end of a string, before or after it's loaded? Does it stretch? Are you using different weights in different trials? Does the string stretch in the same way? How are you measuring to the centre of weight when the weight itself gets in the way and hinders you knowing exactly where the end of the string is? Or do you choose the centre of mass of the object at the end of the string to mark where the length is that we're measuring? How do you know what the error is in timing the swing? And now we have two known errors, the error in measurement of length and the error in measurement of swing times. Do these errors add up? Are these errors correlated or uncorrelated? Are they random or are they systemic? Depending on the answer to those questions, we have to account for the errors in different ways. Is the timing device inaccurate or imprecise, or both? If it's inaccurate, is it so in a reliable way or in a random way? That is it always running slow, or does it run slow sometimes and run fast other times? So I ought to mention, accuracy is how close to reality the measurements comport. Precision is the range of a set of measurements, how well those measurements agree with each other. So an instrument can be precise, but inaccurate. Precision is no guarantee of accuracy. So the bathroom scales might show the same reading when a person weighs themselves in quick succession, but it could be out consistently by, say, 3 pounds, in which case the reading is precise, but inaccurate. And then other complications, will air resistance be a factor, or friction in the bearings of the pendulum? Will that contribute to our uncertainty? If so, by how much? What's our level of uncertainty? And that's always the question. What's the uncertainty? How sure, how confident can we be in the conclusions based on our measurements, which have inbuilt errors? So the uncertainty of a quantity is the range within which we believe this quantity to lie. Or lie, anyway. So the bods in science, in their specialised units, labs, whatever, they get to work out all these issues. This is the hard part of science. A, designing the experiment to test a claim or hypothesis, and whether it's, what we'd expect to see if it's true, what wouldn't we expect to see if it's true, what would we expect to see if it's not true, and what wouldn't we expect to see if it's not true. And then design those experiments in a way to remove confirmation bias and other cognitive blind spots, and then somehow determining the inbuilt error so that can be accounted for. So coming a little further back to reality, let's take an example of gravity. Suppose we want to work out the acceleration due to gravity, and I'm going to do this using a simple ball drop from multiple heights, different heights. All models are defective in some way and often contain ambiguous cases. Some are included when perhaps they shouldn't be, and some are excluded when perhaps they ought not be. And what makes matters worse is that some of the laity have grabbed onto a false insistence that science is 100% accurate and absolute, and what they've really only latched onto is really only shortcuts that scientists use as a convenience to talk about concepts. It's not that they have any specific meaning, it's just a useful shortcut. So I want to stop by a couple of these before we move on, just to cover off the basic idea and consideration of statistics, and a few examples of instances that are scientific shorthands that are actually meaningless but often repeated. One quick example is fish. It's really a meaningless term nowadays. It's so broad. I mean, what does it mean? Water-dwelling animal? But that includes things like octopus and stingrays. What does it define? It's, so we all kind of know what it means, but it has no specific scientific meaning. I've noticed other disingenuous extrapolations are made when, say, for example, a chart shows some characteristic that's been broken down into male and female into, 49 and 51%. And since these are up to 100%, this is proof that there are only two genders. Not so fast. And that's another thing. Summary results are often a broad description pertinent to the point or conclusion, of the matter at hand. Be wary of, using statistics in one report or the conclusions or the methods, and to try and transfer those onto something else that it wasn't intended to be used in such a way. I know that sounds a little bit disingenuous, but The case that I always make is, for example, where somebody's been murdered by being bludgeoned to death by the butt of a rifle. Is that a gun crime, or is it blunt force trauma crime, or both? So it might well go into the table for gun crime. It may well also go into the table for blunt force trauma crime. When you do your analysis, you have to be aware, and you have to know to correct those tables, because if you count the same crime twice, when you add up how many gun crimes are there, how many blunt force trauma crimes are there, and you add those two up and say that that's the conclusion that how many crimes there were, they've actually included a data point twice. So depending on what question you ask of the data, you have to know how the data tables are constructed, and you have to remember to take those duplicates out. Right? And so this is what I'm saying, is that you can't just necessarily add up the conclusions that there are so many gun crimes and there are so many blunt force trauma crimes, therefore if I add those two together. No, some of them might overlap. Same thing with this example of 4951. The actual figure might be 48.51 and 51.02, and that leaves, a fraction of the other percent for the much rarer cases, which are a large number of people, but as a percentage, very, very low. Another example is the 97% match of genetic code with chimps or great apes or whatever it is. While statistically not false, it's also problematic. Scientists don't really have any use for this fact. It's a useful metaphor almost to intuitively spark interest in a laity. In a similar way, it can be said that the real great invention of English was the 26 letters of the alphabet, and since then it's just a remix and a mashup of what's already there. Is it new? Well, yeah and no. It depends how you count it. Same with genetics. Is a rearrangement new information? Because it contains the same code but rearranged in a different way. And where we have one set of sequences that's copied, say you've got 4 characters that are copied, is that 4 changes or is it only 1? Because it's a duplicate, one duplicate, but it contains, so 97%, it's kind of right, but not really useful. And just to get it off my chest, because I can't resist, flat earthers. Okay, granted. Those textbooks, the ones that have composite photos and 3D and CGI renderings, are not science documents. They are, to the most part, factually correct to the intended audience, but also meant to be awe-inspiring and inspirational to attract people's interest in learning more about these things. I mean, I don't know, 4th, 5th graders, you're not going to give them some peer-reviewed paper to read. They want to see pretty pictures and see, so there is a thing called space, and there is a thing called planets, and they orbit the sun in approximately, let's say elliptical way. And it's, again, it's 97% correct, but that's the thing. In the small error, in the defect in the model, there is something to know, something to learn. Regarding data then, and collecting it, it's worth pointing out that there are several recognised programs for collecting or surveying data, and the larger the sample size, certain types of errors are smoothed out. The bigger the data set, the better able we are to detect real effects. And the only way to perfectly smooth the data is to, should I say smooth the data or smooth the errors? See, this is the problem with, got to be so careful in the language. I think it's correct to say smooth the errors. Is to take a sample size equal to the same size as the entire system. And to do it, you have to do it all at the same time. This is known as a census, and although smoothed errors are still present, you just can't get away from it. And sometimes it's impossible to take a census anyway, and usually very expensive. So again, you've got to weigh up the pros and cons. Is a census the only way to get you the data that you need, or is there another way of getting the data that will do the job at a fraction of the price and inconvenience for everyone? So the point of doing this, and being so precise, is to remove those errors, or at least to know the scope of those errors, thus to reduce risk and uncertainty in the predictive capability and utility of the knowledge derived therefrom. So assuming that done, we then have insight, we have a working model, perhaps even 2 or 3 working models with predictive capability, with known limitations, with known application criteria, and can then apply the knowledge and the insight and the analysis into a design process to maximize benefits, I presume, and then we're in business, so to speak, to create, the implementation from design to create assets that hopefully bring benefit. Now, which model we use is a function of application. ease of use, and known limitations. Even in the case of equivalent models with the same assumptions, we'd always prefer a model, by the way, with less assumptions in it, even if it has equivalent utility. We might even prefer models that are logically equivalent, but we might prefer one for psychological reasons. It's easier to explain. It's easier to convey. More people in our organisation have relatable metaphors to one of the models, that kind of thing. So a census then, expensive. Perhaps we can use a smaller sample, but what kind of sample, and how should we select the subset? So right here we encounter our first problem, selection bias. Cool, blimey, this video is going to be about half an hour. But, okay, so selection bias. Right, so perhaps we're lazy. Perhaps we take the sample too close to where we live for convenience. Perhaps we recognise this as flawed, and we think that if we drive to somewhere remote that we don't know anything about, we can remove our bias. So we're in the business of surveying roads and highways for traffic patterns, but we didn't consult the council, who've just closed off the road we've visited for repairs, but we didn't know. Obviously, that's going to skew our results. Perhaps we just assumed that this was a quiet road. We didn't know any better because it was quiet when we got there. It was quiet whilst we counted the cars. And at one end, the road closed sign was around a blind corner and we didn't notice. What about random sampling then? We hear about this method too. So suppose we want to get a rough idea about the length of TV movies. We could sample them all and take the average. Arduous. Or we can buy something like a TV schedule, TV guide, TV listings, and select films at random, hopefully not swayed by the titles or ratings of which to include in our sample. And how do we overcome that bias? Well, we decide up front how to make the selection. We decide that up front we're going to give each film a number. So let's just say we have 50 titles from our listing or whatever, which of course itself is a subset, but we'll just gloss over that for the moment. And we relabel them 1 to 50. So no names, no famous actors, it's just film 1, film 2, film 3. And then we have a random number generator, problematic of itself, and generate 10 numbers. And of each of the random numbers generated, we select the corresponding film with a matching number. That's now for inclusion in our set. Systematic sampling is to use the same sample set as an example, where we generate one random number, and then we select the film in the TV guide or in our list at that ordinal position. So, throw a die, number 5, right, we go straight to film number 5. That's our first sample. And then we skip the next 5, and then where we land is our next sample, and then we skip the next 5, and where we land is our sample, and we keep going until we've got the number of samples we require. If we get to the end of the list, we just start from the start of the list minus the offset remaining in our random sample. So if we're doing 5s and we get to the end of our list and we count 1, 2, 3, we go back to the start of our list. Position 1 is now 4, position 2 is now 5, and that'll be our next sample. Then there's stratified sampling. In this case, we would organise the films according to some category, let's say film rating, 18, R12, PG, whatever it is. And then we select proportional random sampling from each category. So let's say we need 20 samples, whatever that's decided the sufficient number. And in the certified 18 films that composes 50% of the films. Then we need to sample 10 films from that category to get a weighted average sample, and then apply similarly to other categories. So if the R-rated films made up only 5% of the number of films, then 5% of 20 is 1. So we'd need to pick one film from the R-rated category. I think that's what we're talking about. So that's another way to do it. Cluster sampling is a method typically used in marketing research. This is where we would cut out a section of the TV guide or draw a big circle around particular areas. Then we cut those into smaller sized portions or groups or clusters. Then we would randomly select clusters to use, and perhaps then either sample all elements of each selected cluster or perform a second stage selection and random sample elements from the selected clusters. So lots of different ways of doing it depending on the applicability and suitability. And while I'm at it, I've also noticed lack of general understanding of what evidence is and what facts and data are. I hear people talk about evidenced data. I think, what the fuck's that? To be clear, data, some information. Maybe right, maybe wrong, we don't know, it's just information. Facts, verifiable points of data. So, is the data verified? If yes, it's a fact. Evidence, a body of objectively verifiable facts, that's what facts are, that are positively indicative of one available position over any other. Therefore, the same fact cannot be evident of two different mutually exclusive conclusions at the same time. If the same facts could be true in different or alternative hypotheses or propositions, then they are just facts. They don't become evidence until it indicates one position or eliminates another. And I kind of think about court cases. You don't bring in evidence. you bring in facts, data, you bring in exhibits which are tested. And what results is the evidence. Yeah, I know there's lots of rules about rules of evidence and all that. I don't even pretend to understand or know what that is. So it should go without saying then that every model, no matter how good, is not free from error. There are no perfect models. And a big area of study in science is error. And this is really what statistics is. It's what's the difference between what the model says reality should be and what reality actually is. What's the residual phenomena left unexplained? And this is where scientists get excited because it means there's something new to learn. So I wanted to keep this short, and it's actually a portion of a much longer piece I'm working on, but I wanted to get to curve fitting, and we still have a bit of work to do to get to that. So again, back to gravity. So let's suppose that we notice when objects fall, they pick up speed as they do so, the very definition of acceleration, a change in velocity over time. And strictly speaking, velocity has a directional component, but conveniently our experiment is going to measure things dropping straight down. So we've designed an experiment already to remove one difficulty. Nice one, that's cool. And from first principles, we can derive equations of motions, and the one we were interested in is s equals ut plus half at squared, where s is distance, u is initial velocity, t is the time, and a is the acceleration due to gravity. But since we're dropping objects with a starting velocity which is 0, then u is 0, and anything times 0 is 0, so the first term, ut, will always be 0, so we can drop that off in this instance. Nice, more simplification. Now we can rearrange the formula to find or isolate t, or time, and now we have a model that gives a prediction about the time it takes for an object to drop a certain height from rest velocity in a gravity well. So let's just take a wild stab in the dark. I don't know, let's just say we think that acceleration due to gravity on Earth is 7 meters per second. 7 meters per second squared. That is to say that for every second an object's falling, it picks up another 7 meters per second in velocity in the downward direction, in alignment with the gravity well, being overly technical. So here's what a plot of that would look like. This is our expected result. Always good to do the expected bit first, because if we do the experiment first, there's always a temptation to draw different lines from our expectation beforehand. So, be honest. Have intellectual honesty. This is the model. This is what it predicts. Draw it in. Commit to it. Do that bit first. Then do the experiment. All right. So let's do the experiment. I'm going to go and pretend I've done the experiment just to keep things. I'm not really going to do it, but let's do some tests then. And from various heights, half meter, 1.5 meter, 1.75 meter, 2 meter, 3 meter, 4 meter, and say 10 meters. And we take the timings and see what we get. Now, I should just point out that for brevity here, this is really oversimplified, because in a real lab we'd repeat each drop at each height several times, probably take an average for each drop, again see smoothing out the errors, and then measure standard deviation, which is the measure of the amount of variation in the set of timings related to the average or the mean. And we'd do the same for the heights, by the way, because we're always going to have error in measuring our height. So in the short version, I'm skipping out the error completely, which seems an outrageous thing to do since that's the point of all this, but I want to get to line fitting. No joke, doing the error bit could take another half an hour, 45-minute audio video. So here it is, here's our results in table form, and then we'll put them on a chart. And let's say yellow dots is our observed data point, red is our prediction, having the guess with 7 meters per second. So here's our measured data points. No error bars are shown. I want to emphasize this is quite poor. In real science, if you tried this, you'd get kicked out. You just wouldn't do it. If you ever see, a paper without errors or error bars, you pretty much ought to discount it. Anyway, but this isn't an endeavor to calculate gravity. This is an endeavor to demonstrate what line fitting is and what data collection and sampling is all about. It's just to get a kind of gist of it. Anyway, so here we have the points. Now we can notice there is difference, and we can measure this difference. Again, in the real world, the differences would take account of the uncertainty in the measurement, but we're just doing we're assuming differences between the centres of these points, but one would have error bars on, which would carry through to our calculation, but I'm just omitting those to keep it nice and simple and straightforward. Just to be clear, making that point clear. So the difference between these 2 points is known as the residual value, something to understand, something to learn. And we use little r as convention to denote the difference. Now, again, when it comes to taking measurement, we might be over on one measurement and under on the next. And so we might think that we ought to add or average our errors to get a sense of the uncertainty in our measurement. But of course, the problem is that if we measure over on one measurement by 1, and we measure under by 1 on another measurement, if we average out the errors, we get 0 error. But this just intuitively can't be right. If anything, we want to add to the absolute values of our errors, in which case for these 2 measurements, we're out by 2 units of measurements. Turns out we can actually do better than this, and it comes back to standard deviation. So instead of adding up the absolute values, making negative errors positive and adding up all positive values, we actually add up the squares of the differences to the mean and divide by the number of samples. Yes, for statisticians watching, there is added complexity here, whether it's the number of samples or the number of samples less 1. Yeah, it's either n or n minus 1, skipping some details. And then we take the square root of that lot. So you'll appreciate that squaring any number, the result is going to be positive. Minus 1 times minus 1 is plus 1. So the square root of 1 has 2 answers then. Yes, it does. 1 and minus 1. Another story. Anyway, we can take a slightly different approach, which is what this line fitting is all about. So let's just note the difference, the measured difference between our theoretical or so-called fitted values, as predicted by our guess of 7 for G, and our test results. And in some cases, we might have negative results. So we're going to square all the values and then just sum them, and we get a number. Okay, again, something else to learn. A number on its own, data point, a single fact, is almost meaningless. I've seen too many online arguments that leap from one data point or one fact to a conclusion that demands immediate policy. It's rather disingenuous, and that's being charitable. So I weigh 100 kilos. Maybe I do, maybe I don't, and I have no idea what the error in that guess is. Meaningless. If I said I'm 4'8", that might mean something very different than if I said my height was 6'6". It's all to do with comparisons. So the value of r squared, I haven't computed it when I'm doing recording, but it's on the screen. Let's take another guess for gravity. This time, instead of 7, let's say 11. And we draw another fitted curve. And again, calculate the residuals. And again, take the sum of the squares of the residuals to get r squared. And we find that this r squared, is smaller than the previous r squared, and the fitted line seems closer to our data points. Alright, cool. Now we know what we're doing, we can speed up the process. So let's plot a new chart that just shows the r squared values against our guess for gravity. So r squared on the left, gravity across the bottom. And let's do this for integer values of G, say from 7 to 12, so 7, 8, 9, 10, 11, 12. And we again fit the line, we measure the distance between our observed results, and we'll get an r squared value for each different curve fit of our guessed value for G. And then we plot r squared against G, this is what we get. And we can see there appears to be a minimal value, and if I've done some back of the envelope calculations, as I say, I've not done it prior to recording, but I'm hoping that the value for G shows between 8.5 and 11-ish. So the minima of the error seems to be between those two values, and I think we can get a better idea of where it's going to lie by eye. But we can repeat this curve fitting for smaller slices of G. So instead of taking integer values, perhaps we can take half integer, so steps of 0.5 between, say, 8 and 11, so 8.5, 9, 9.5, 10, 10, 10, and so on and so on. And then we can again plot another sequence of G against r squared. And now we can do this ad nauseum, and it looks to me like we've got a value of r squared, a minimum value of r squared. And there's a lot more to this r squared business. We're going to start doing all sorts of tricks and maths on r squared values and fitted lines, and sometimes minimum values don't necessarily mean that it's complicated all to it. But anyway, this is an illustration. So, we can eyeball it and say it looks like we have a value for G, or a small range for G, that appears to be consistent with the test that we have done. It would be incomplete to say what we think our value of G is without specifying that level of uncertainty inherent in this experiment and in our measurements. And so I'm not even going to start by bad habits by saying what we ought to conclude G is from this chart. We can't do it without the uncertainty. But the point is that we've used residual values, errors, differences, to get close to a range of what G is likely to be. From the measurements we've done, it's the best we have. And that, roughly, is how curve fitting works. A lot more to it, and especially accounting for the error. Now, lay people hear terms like 90% sensitivity and problems with sampling, collecting data and having bad actors, and indeed the literature sent out with the UK's random COVID sampling said specifically, do not let anyone else do this test for you. Why? Test is a test. Well, no, it's not. Because they have profiled with care their sample. They have selected carefully the socio-demographics. They have gone through medical profiles and medical histories of people they have sent these samples to. They know the errors in these models. They're building their sampling techniques to smooth out these errors. And again, it's a conflation to confuse smoothing out errors with changing the data or fixing the result. Because line fitting sounds like fixing the result, doesn't it? Anyway, I hope this has brought some level of confidence and understanding to the kinds of things that are involved. And this thing with gravity, we're only measuring two things, timing and height. When you get into linear regression and you're trying to factor many variables, the line regression gets complicated. I should perhaps just add, I'm sure we've all done it at school. You get many data points, and then the teacher says, okay, draw a line that's roughly through the middle of those data points. All right, cool. We can eyeball it. But, what the software does to fit the line, given data points, is it will work out many different R-squareds for many different lines. Some of those lines, or all of those lines, ought to go through the uncertainty of the error bar represented in each data point. So the computer can go through many different lines, or at different angles, with different numbers going through different quantities of error bars, all the while calculating the R-squared for each trial of a different line, and then depending on what you tell it to do, i.e. fit for best error or fit for least R-squared, it will draw you a line. Anyway, that's enough. That's a wrap. By the way, just to add another thing, this is actually the basis for artificial intelligence and machine learning. So instead of finding, say, a linear regression, which is like a straight line through the data points, as it were, they'll take many, this is the whole premise of big data. So let's just throw up on a chart here a couple of different dimensions. Let's say these data points that we've accumulated on some label, I don't know what we would call it, that is a measurement of many different metrics of photos of dogs. And let's say we also have many metrics or data points that we've analysed from pictures of cats. And then if we plot these metrics, let's keep it really simple. It's actually in many dimensions when they do it for reals. But let's just say we've got 2 dimensions here. And if we plot blue, that gives us that perhaps a human being is evaluated as these are images of dogs. And if we code dots are red, where a human being said these many images are actually cats, when we look at what big data has analysed as coincident points and then run an analysis to find out what the difference is, basically it's trying to work out a formula for a line that goes through these 2 data sets with sufficient certainty to be able to say, haha, this is a dog, that is a cat. So yeah, this is the basis of all the things that we're doing right now.